Let's see step by step how to use the integrating factor. Solve t squared plus 1 dy dt equals 6t minus 3ty. In order to solve a linear equation, you first have to put it into the exact form y prime plus p of ty equals g of t. There's a couple of reasons for this. First of all, you don't know if your equation is actually linear unless you can put it in that form. Second, the integrating factor and the whole method I'm going to show you relies on having the equation in this form. So let's do that. I need to get all the y's over on the left-hand side, so let's add 3ty to both sides to get t squared plus 1, and I'm just going to call dy dt y prime to kind of streamline things. And then I'm adding 3ty to both sides, so I have equals 6t. I also need to make sure that the y prime doesn't have anything multiplying it. So let's divide out the t squared plus 1. Remember, we have to divide both sides of the equation, and also on the left-hand side, remember that t squared plus 1 has to divide each term. So it cancels out the t squared plus 1 on the y prime, but we're going to have a t squared plus 1 in the denominator for our y. I can see now that this is linear. I have a y prime with nothing attached to it. I have stuff with t's multiplying the y. And on the right-hand side, I have nothing but t's. I can see from this that the p of t in our linear equation format is 3t over t squared plus 1, because that p of t is the thing multiplying the y. Now we're ready to compute our integrating factor mu. Mu is e to the indefinite integral of p of t dt. So I need to know what the indefinite integral of p of t dt is. Well, we just said that p of t would be 3t over t squared plus 1 dt. I'll need a u substitution. So let's let u be t squared plus 1. Then du would be 2t dt. So I see that what I'm going to put in for the t dt is 1/2 du. Let's bring the 3 out front. Then the 1 over t squared is going to be 1 over u. The t dt is 1/2 du. I'm going to go ahead and put the 1/2 out front also. So we get 3/2 ln of the absolute value of u. And we don't need a c in this context. The reason we don't need a c in this context is we don't need all possible antiderivatives of p of t. We only need one of them. So I'm essentially saying, okay, I'm going to just have my c be 0. Anyway, going on, we do need to put back in what u really is. U is really t squared plus 1. And then notice that t squared plus 1 has to be positive, so I don't actually need the absolute value bars here. So mu, which again is e to an antiderivative of p of t, and our antiderivative is 3/2 ln of t squared plus 1. So that's our mu, but we can simplify this, and we want to do that. We don't want to leave it in this form. So let's realize that this is the same thing as saying e to the ln of t squared plus 1, all of that raised to the 3/2 power. Right? Because when you have a power raised to a power, you multiply the powers. In other words, I'm using the rule that if you have anything to a power raised again to a power, you multiply the powers. But we don't actually want them in the multiplied form. We want them in this form. Why? Because now we can simplify. The e and the ln will cancel each other out. So I'll have t squared plus 1 raised to the 3/2 power, and that is my mu. Next step is to multiply both sides of the equation by mu. And when I say equation, I don't mean the original format of the equation. This is another spot where we have to use this form of the equation. So I'm going to be multiplying this equation by t squared plus 1 to the 3/2. That will give us t squared plus 1 to the 3/2 y prime plus 3 t squared plus 1 to the 3/2 t over t squared plus 1 times y equals 6t t squared plus 1 to the 3/2 power over t squared plus 1. Let's simplify. That'll give me t squared plus 1 to the 3/2 power y prime plus 3 t squared plus 1 to the 1/2 power times t times y. Do you see why that is? The t squared plus 1 in the denominator has an invisible 1 power, and so I just subtracted the exponents using the rule that hopefully you know, that a to the n over a to the m equals a to the n minus m. Then we have equals 6t, and again canceling by using the rules for exponents, I get a t squared plus 1 to the 1/2 power. The whole point of multiplying by the integrating factor is that the left-hand side of our equation should now be in the form mu y prime plus mu prime y. This would mean that the left-hand side is the same thing as d dt of mu y. But things get pretty complicated when you're multiplying by an integrating factor, and I personally always check to make sure that my left-hand side is in fact equal to the derivative of mu times y. So let's do that now. So our mu was t squared plus 1 to the 3/2, and then we have our y. Using the product rule, I'll have 3/2 t squared plus 1 to the 1/2 power times 2t times y plus, and this time I won't differentiate the first factor, so I'll keep the t squared plus 1 to the 3/2 power, and differentiating the y gives y prime. Let's simplify that. So In the first term, the 2's cancel, so we have the 3t squared plus 1 to the 1/2 power times t times y plus t squared plus 1 to the 3/2 power times y prime, and that is exactly our left-hand side of the equation, just written in the opposite order. So we are good on that. We haven't made any mistakes with our integrating factor or our multiplication or our simplification. We're ready now to integrate both sides of the equation, but I'm going to write the left-hand side in the form d dt of t squared plus 1 to the 3/2 times y, and then we're integrating that. The right-hand side of our equation was 6t times t squared plus 1 to the 1/2 power, and again we're integrating that. On the left-hand side, the integrating and differentiating cancel each other out, leaving us t squared plus 1 to the 3/2 times y equals, and on the right-hand side I'm going to need a u substitution, so let's let u be t squared plus 1, then du will be 2t dt, so I'll be putting in a 1/2 du for the t dt. I'm going to bring the 6 out front. The t dt turns into 1/2 du, and I'm bringing the 1/2 out front. And then inside we have u to the 1/2. So integrating, well, let's simplify. The 6 times 1/2 is a 3. And then integrating, I'm going to have u to the 3/2 over 3/2. So at this point we have t squared plus 1 to the 3/2 y equals 3 divided by 3/2 is going to be 2, just invert and multiply. And then I have u to the 3/2, but u was just my name for t squared plus 1. And now we do finally need the c, because we're now at the point of giving the general solution to the differential equation. Last thing we need to do is solve for y. So let's divide both sides of our equation by t squared plus 1 to the 3/2 power. That gives y equals 2 times t squared plus 1 to the 3/2 power plus c over t squared plus 1 to the 3/2 power. We can actually clean this up by splitting this up into two fractions. And yes, that t squared plus 1 to the 3/2 did have to divide everything, including the c. Anyway, if we split that up into two fractions, I'll have 2 t squared plus 1 to the 3/2 power over t squared plus 1 to the 3/2 power plus c over t squared plus 1 to the 3/2 power. So our final simplified answer for y would be 2 plus c over t squared plus 1 to the 3/2 power. That was a long problem, wasn't it?